Hello, hi everybody. I'm Alejandro Castro and I'm going to talk about AM and FM modulations, explaining basically the meaning of them and how they work on any kind of signal known as a message. This will be kind of an introduction for our project, who is a superheterodyne receptor. Okay, so starting with AM modulation. Mathematically, how we create an AM signal is by choosing a message and multiplying in time domain with our carrier signal. Our carrier signal is always going to be a sinusoidal wave. After that multiplication, we just add the carrier again to our result. And finally, that expression is going to be called AM signal. That's going to be the AM signal, this right here, and we got here message and we got here our carrier. First of all, we just multiply them, both message and carrier, and we got right here our result. Then we have to add again our carrier to this result, and after that we're gonna have our AM signal conformed. Okay, so amplitude modulation works by changing the amplitude of the transmitted signal in relation to the information being set on that signal. Once the signal is being modulated, we can control one parameter called modulation index. We can look at modulation index right here. On the first image we got a 50% modulation index. Second, right here we got a 100% modulation index, who's the best that we can get, and we should look for that every time. And right here we got an 150% modulation index, who is a over modulation and is the worst of them. So that parameter called modulation index is what's going to tell us how much pronounced is going to be the modulated signal based on how our carrier modulates our message. Basically, when the modulation index is higher, the modulation is better, because that tells us, or that shows us, all the amplitude changes product of that generated crest, and that's what we're going to look for. Okay, so now FM modulation. Frequency modulation in telecommunications is the encoding of information in a carrier wave by varying the instantaneous frequency of the wave. That frequency variations tells us when we got zeros or when we got ones, for example, like here. Here we got an example of any FM signal. In this case we got like a sinusoidal one. We got right here one frequency and right here another frequency. Both are different, and we can tell that one of them, when we receive one of them in our receptor, we can tell that phase is going to be a 0, and we can tell that the phase who got the other frequency is going to be a 1, and that way is how we're gonna use the codification to get a conversation between 2 points. So then we got two types of FM signal. We got narrowband FM and wideband FM. The difference between them is that narrowband FM signals got a lower bandwidth on the message, and wideband FM signals got a higher value on the wideband message value. We got here how we can produce, how we can create a narrowband FM signal, and we're gonna talk right now about wideband FM. Finally, on wideband FM case, who got a higher bandwidth on the message, as I said before, we can get that signal right here by applying the Bessel table right here. Bessel table is a function where we can express the FM signal as a sinusoidal series with the Bessel parameters. That Bessel parameters represent normalized voltage and help us to calculate bandwidth for some different methods. Right here we got our sinusoidal series, and right here we got our FM signal expressed in function of that Bessel parameters. Who are these ones? These parameters right here. After that, we have 4 forms of how we can get that bandwidth using that sinusoidal series with Bessel. We got first of all right here Carson way. We got right here this one called the essential one, and that's how we called this formula on communications section. And we can get some two other forms if we got beta, bigger or smaller. If we got a bigger one, we use this form, and if we got a smaller one, we use this form. But we established in the past that the better of all forms is the Carson one, because that gives us a more value of the bandwidth of the signal.
Hi, my name is Cledraman Guerrero. I will explain the Superheterodyne Receiver. Firstly, I will explain the reason for using this type of receiver. When Haber electromagnetic signals AM and FM were started, in the beginning were few. It was possible to offer a circuit for each frequency that was wanted to tune. These circuits were in cost economic because they did not require a high order and weapons. But as the amount of signals in the air increased, and then for have the possibility to tune the all, we abandoned a circuit whose width of them could be varied. That adjustment in the receiver did not have real impact in their economics, since although it was variable, it was reduced of several circuits for the multiple tuning to a single circuit that did the same, and in the same way it was not necessary for it to be of a high order since the dark band was extended loop. Then, when this type of technology for the informational and entertainment use, the band began to be reduced, of the until arriving at the point that all the stations were one next of the other, thus increasing the order of the variable filters to active. QH was carrier without interference from the one next to it. This increased the cost of the filters, making the service also more expensive. And that's where the Superheterodyne Receiver arrays This idea is to take all the signal to a single call center frequency. Image frequency, text frequency is a different amplitude modulation and frequency modulation. This way, we will have a variable filter in the input with this low order. This data is economical and thus objective is surely to reduce the power of the noise entering the system. Then to the output of this filter, we will have a mixer, which will have a frequency equal to the sum of the frequency of the carry and the image frequency. Thus the image frequency filter is called the order high. And thus to get the best filtering signal we want to tune. Thus solving the problem of the narrow dark big white affects filter. Next, I'll show you some graphics to better understand this technology. For the case NM, we will have a bandpass very bold filter, low order and good width. Bandwidth is 10 kHz. Could this be higher? Yes, but we will increase the power of the noise that enters the system. To the case FM, the filter have a bandwidth of 200 kHz. As we vary the central frequency of such filter, we entering into the system any signal that during that momentum set of the width of the filter. And by mixing the center frequency of the same to the frequency of the carrier we want to tuning, the desired signal will vary the system. Subsequently, it will be mixed with a sinusoid whose frequency is the one I mentioned above, leaving the desired signal center of the image frequency. Likewise occurs with the frequency modulation. Then, we can place a filter of high selectivity and fixed. That is, in order to properly filter our signal, it with low waves frequency equal to the image frequency. But the bandwidth will depend on the type of modulation. If we then mix that again with a sinusoid whose frequency even image frequency, we will take our signal to best band recovering our signal.
Hi, my name is Sharon Gruber, and I am going to talk about the Superheterodyne Receptor in LabVIEW. My explanation will be focused about the user interface and its management. Well, here we have the project Receptor Superheterodyne, and here I am going to tell you how it works. This is an interface handled by the user, and in the top of the screen here we have three tabs: the transmitter, the channel, air, and the receptor Superheterodyne. For manage this project, you will have to take some decisions that will help you to modulate the signal and then receive this one with the Superheterodyne receptor. So first you click here in transmitter and they will appear two tabs: amplitude modulator and frequency modulator. So the first decision you will have to take is how do you want to modulate your wave, in amplitude, in frequency, or in both ones. So if your choice is only modulated in amplitude, you will click here in this button, this means AM on, and if you click again, this means AM off. So I will repeat. If you want modulate in amplitude, only you have to click here and the button will be green, and you have to off the dark button. You have to you don't have to click this button because you only want to modulate in amplitude. Well, the second decision that you have to take is that you have two options for transmitting waves, where only one option will be chosen. So the first option is generate a waveform with a waveform generator. So we click if you want these options, this option, you click here and the switch is up. That means waveform, okay? And if you don't want generate a waveform, then you have to down the switch, and that means a sound. For example, a song. Well, first we will prove it with the waveform. Well, these panels of here, we will see it with the proof, but this is in time domain, the signal before modulation, the signal generated here with these parameters, and we will see that wave in time domain here and in frequency domain here. When we put the data of the modulation, like the carrier frequency or the modulation index or the amplitude of the carrier, then we will see the modulated signal in time in this one and in frequency in this one. Well, now we are going to begin the test number 1, that is generate a wave, for then fill the data of the modulation and see the spectrums in the panels right here. Well, let's begin with the wave type. Well, first up, because we are going to do a waveform, and here too. Then we decide what type of wave we are going to generate. A sine wave, a triangle. Let's do it with a sine wave if it is of your preference. Then the wave of the amplitude, we are going to put 1, phase 0, and the wave frequency, it goes from 0 to 5 kilohertz. So we are going to put it in 5. The reason is that the voice is up to 5 kilohertz. So the wave frequency could be 5 kilohertz or lower. If you choose a bigger frequency, the superheterodyne receptor won't be working correctly. Well, then we are going to fill the data of the carrier frequency. Remember that we are in the AM case. In this case, AM case, we have a bandwidth of this is the bandwidth, from 535 to 1700. This is a mistake of typing. So if you choose a frequency out of this range, the superheterodyne receptor will not be working correctly. So we are going to put here any value in this range, like 600. Then we are going to put a modulation of the index of 1 and an amplitude of 1. And that's all. So for see the spectrums, we are going to click here to run the program, and we will see in this one the signal before modulation with the frequency that we put here of 5 kHz and a wave type of sine. In frequency domain, we are going to put some if we want to see it closer. So we see that this is 5 kHz right here, and this is the spectrum of in a frequency domain. Then we are going to see the modulated signal. This is in time, and in frequency we are going to see that is centered in the carrier, that is 600. This is a delta centered in 600, and the message, the frequency of the message, that is 5 kHz, is here 600 plus 5, it is 605, and here is, and the message, the frequency of the carrier. So here we have the frequency of the carrier, that is 600, and in the left we have the message translated minus 5 kHz, that is our wave frequency, in 595. So we will keep with the channel in the channel that is the air. We are going to see what happens after the transmitter. We click in channel, and this switch is for noise on and noise off. What happens when the signal has already been transmitted? Well, the signal is in the air with noise, like in the real life. And in this tab, channel, we can see above of the page the signal in the air without noise, and under this we will see the signal in the air with noise. It depends if this switch is on or off. If the switch is up, the noise is on. If the switch is down, the noise off. Like we see, we are going to turn on, and we will see the spectrum in the time domain without noise and with noise, and in the frequency domain. First, before see the superheterodyne receptor, we are going to fill the data of the if-m case, and we are going to fill it in the transmitter. Then we will see the signal in the air, f FM with noise and without noise, and then we are going to see the superheterodyne receptor for the FM and AM case. So let's back to the transmitter to fill the data of the FM signal, like this. Let's back to the transmitter, click in the frequency modulator, then click here to FM on, then fill the data of the signal, the frequency 5 kilohertz with amplitude 1. Then we have to fill the data of modulation, like the KF. We're going to put 2 on the carrier frequency. Remember this, the carrier frequency will be in the bandwidth commercial of AM, that it goes from 87 to 107 megahertz. So the carrier frequency will be in that range. So let's fill here the data of the carrier frequency. We are going to put 88,000 kilohertz, that is the same of 88 megahertz. So we are ready to compile the program. So here we see the signal in time before modulation. The frequency we choose 5 kilohertz. Then we have the signal modulated like this. We see the variation of frequencies, and we see the spectrum in frequency domain with a center of 88 megahertz. So let's see the tunnel and how the signal FM looks in the air without noise and with noise. Well, we click here in tunnel layer, we up the noise, and remember, put this in only FM to see the signal and FM in the air, and the signal in the air without noise look like this. We see the variations of frequencies, and the signal in the air with noise is like this. So if we see the spectrums of frequencies, we can see the same graphic of the part of the transmitter, the frequency of the carrier in 88 megahertz, and it looks here. We look here. So now we are going to see both signals AM and FM in the tunnel with this option of here, AM and FM, and then we are going to see both signals in the receptor superheterodyne. So if we choose this option, we will see the add of a signal AM plus a signal in FM, a signal FM. So we are going to see that adding here in the time domain, FM plus AM signals, and with noise we see here, and we are going to see the spectrums of frequency. So in the spectrum of frequency, we have to observe that we are seeing both frequencies of carrier in this one. These belong to the AM signal with a frequency of carrier of 600, and very far away from this signal will be the spectrum of the FM signal that we are going to see in a little moment. And we are observing that they are too far and they will not be overlapping because they are too far than the other. So we can see this one here. We can see it here with a frequency of carrier of 88 megahertz. So now it's the moment to see the receptor heterodyne with both signals. So let's see it. So let's start with the superheterodyne receptor and the handle of this. So the first thing you have to do is know what type of modulation you want to recover the signal. So you click here in FM or AM case. So we choose first FM. The toner, you had to put it in the carrier frequency. Remember that we choose 88 megahertz, and the volume will be in a value different than 0. So we'll see the recovered signal in time and in frequency. And we have this, the in time, that is the recovered signal in the time domain, and in frequency domain we can see the recovered signal with the center in 5 kilohertz. That is correct because we put here 5 kilohertz. So let's see the AM case. So we click here, we stop the program, and you click here in AM case. To see the recovered signal in AM, you adjust here the frequency of the carrier that we use here, that is 600 kilohertz, and then we put the volume in 10, and we see the recovered signal in the time domain and in the frequency domain. We have to observe that here we have a response of the filters. This happens because we are using values very small. We are not working really with kilohertz or megahertz because the processing of the program would be really slowly. So we are working really in the block diagram with values in hertz, not in kilohertz and not in megahertz. So this response would be more smaller if we really use kilohertz and megahertz, but we can't use that values. So we see that this is very noticed. So when we go to the frequency domain of the recovered signal, we see that is centered in 5 kilohertz as we see in the transmitter. So this is the end of the explication. I hope you have liked the explication and you have learned about the superheterodyne receptor, our program, how to handle it and how it works. Remember, like this video, and bye bye.